So we need to define the boundary for more than just two cells of a cell complex. We're going to do 1 cells, we'll do 0 cells, later on we'll do 3 cells. Any way we define it, though, we want to ensure that the boundary of a cell comes out to equaling 0. And remember, it works that way naturally for sets. The boundary is empty. But now we're talking about groups, and we want to make sure that when it came out empty as a set, that for a group it comes out 0. To do that, for the 2 cells, like A, we need to define the boundary on line segments. We give the line segment an orientation, like here's a little a line segment. It goes from y to x from our example of the real projective plane, and it happens to be oriented from y to x. We define that boundary, the boundary of that little guy, to be x minus y. It's a natural way to do it. We choose to make the arrow point from negative to positive, and so you start with the endpoint x and subtract the starting point y. So the answer to the boundary of a line segment is the 2 endpoints, and I write their names down, not dots in this case, because we're already using disks, D0 disks, 0-dimensional disks, points, as generators of a group. We're going to describe that group very soon. We're building up to it, but on page 3 we define it. So now let's see that we get what we want. First of all, the boundary is going to be defined to be a homomorphism. In this case, we could even say that it's linear because we're talking about an additive operation, commutative operation. So to check that we get what we want, we take the boundary of A, which we already found inside of the parentheses, negative a plus b minus a plus b. And then we use the homomorphism property, or linearity, to distribute that boundary operator, boundary function, over the whole thing and pull out the minuses. And then for each of those line segments, we do what we just defined and write down their endpoints in the right order. So for A, it's x minus y, and for B, it's also x minus y. Notice in the picture of P2, B also goes from y to x. So this time it becomes 0 too easily, actually. But double check it. It has negative x twice and positive x twice. Negative y and negative y shows up twice, and then positive, the negative y shows up twice. So altogether, it comes out to be 0. So here's some more examples for comparison, and there's a note on the side. So for just a circle, you can make that into make it as a cell complex by having a single 0 cell, the dot, and a 1 cell that's both ends glued to it. But then if you use the definition of the boundary of a 1 segment, or 1 cell, or a line segment, then it's x minus x, since they both have the same endpoint, or they're both glued to the same thing. And that comes out to 0, just like it should. Here's another disk, D2. This one is an actual disk, though. It's not, doesn't have any gluing of the edges. But we do still need arrows on the edges so that we can see what orientation is. It's an arbitrary orientation. The arrows here don't actually mean gluing. They're just arbitrary orientations. For the 2 cell that we're looking at, the filled in triangle, we choose counterclockwise again. You could go clockwise and it would work just as well, but you have to pick an orientation of the 2 cell. And then I also have to pick a starting point. That's also arbitrary, but I picked x again. And then following the boundary counterclockwise, you have C going with the arrow, plus B, and then minus A because it's against the direction of the arrow. And notice when we did the boundary of P2 up here, It was following the arrows, but they were also the arrows were also showing how to glue. In this case, the arrows are doing double duty because they're showing you how to glue the edges together, and they're also showing orientation, and that's fine. You just have to know from context what the arrows mean. So somebody has to tell you ahead of time what's going on with the arrows. Are they being glued, or are they just showing orientation? Whenever there's more than one kind of arrow around, it usually means that they're being glued. But here I knew that was supposed to be P2, so those arrows are for gluing and for orientation. And remember, then the orientation isn't completely arbitrary. It's that you can pick the arrows to go any direction you want as long as you keep the space the same. So if the single arrow is pointing up on the left, it has to be down on the right. And if I change it and make it point down on the left, it'll have to be pointing up on the right to make P2. Now finally we check that the boundary of the boundary is 0 again on that last example. We apply boundary to the boundary of that triangle, and we get, after linearity, boundary of C plus the boundary of B minus the boundary of A. And then using the definition of the boundary of a one segment, we have y minus x plus z minus y, and then minus z minus x. Check the double negatives, everything adds up to 0.